Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD fluid mixing using ANSYS watertight geometry. This watertight geometry is a new introduction to 2021 interface. This will be a heterogeneous fluid mixing and we'll be using ANSYS watertight geometry. Let us open ANSYS watertight geometry from the Fluent launcher. This is a very simple geometry actually. Let us import the geometry from here. This is the geometry. For understanding the geometry, let us cut it from front end. You see the model. This is a simple geometry. It is having two different openings. This is one opening and this is another opening. From these two different openings, we will be providing different fluids. And inside this one already from the beginning itself, it will fill up with air. From opening one, we will be providing water at a specific velocity. And from this opening, we will be providing some other fluid. Maybe we will be providing methanol at a specific rate. And finally, you will see the volume fraction of all these things and also their velocity, pressure, distribution, etc. inside this chamber. Okay, right. We need not require any kind of local sizing. This is a simple geometry, so we can update this model. Next to that, we have to generate surface mesh. Surface mesh is being generated. Next to that, we need to describe the geometry. It is having two different entries. One is for water, another is for methanol. From these two entries, we have to provide different fluids, and down we are having one opening that is considered as exit opening. Right. The geometry tells that it is consisting of solid only, and we need to provide fluid domain inside this one. And definitely in this case, we need to provide some caps. And third one, and it is asking, do we need to apply shear topology? Yes, we can apply shear topology. Then describe the geometry. For shear topology, the maximum gap distance is 0.67. Let us apply shear topology. It is done. Next to that, we have to provide caps. That means different entries should be filled up. And after that, we need to provide fluid domains inside. So cap 1 is considered as inlet 1, and the zone type will be velocity inlet. Let us provide cap to that, and we can rename this one as cap 1. Let us cap it. You can see capping is done at this location. Next to that, we have to apply cap 2, that is inlet 2. From that one, we have to provide methanol at a specific rate, and also zone type will be definitely velocity inlet, and we can rename this one as cap 2. Let us update this cap. It is also done. Finally, we have to provide cap at the exit location. Exit is at the bottom side, and the zone type should be definitely pressure outlet, as it is the exit. And let us update that cap at the bottom side. All the caps are provided. Next to that, we have to create regions. That means the fluid subdomain should be provided. We need to provide that fluid domain. So we can see that estimated numbers of fluid region is 1. Let us update that region. In a single fluid domain, we have to provide different heterogeneous mixing. Create region, because inside this one already air will be there. It is showing that two regions are there. One is solid region, that is the container, and other is fluid region or fluid domain. Let us update this region. We are decreasing the numbers of boundary layers from 3 to 2. Let us add boundary layers. Next to that, I'm going to generate volume mesh. with the growth rate of 1.2. Generally, it should be 1.2 to 1.5. Let us generate the volume mesh. We are opting for polyhexagon mesh, and let us update the volume mesh. So volume mesh is generated. We can see here, and you can see two layers of boundary is formed here, right? Next to that, I'm going to switch into solution mode. Before that, we need to have an assurance that the meshing is perfect. It's fine. You can see that meshing has a minimum orthogonal quality of 0.16 and 88,750 numbers of cells were created. So it is fine enough. So we are switching on to solution mode. While initiating this solution mode, first of all, we need to set the units. Let us set length to be in millimeter. In this case, we don't require any kind of temperature. So let us close it. As it is a fluid mixing, we can consider gravity. And the direction of gravity will be y. It will be minus 9.81 along y. We're considering this one as a transient analysis. Before defining multi-phase options, we need to provide materials. Let's provide materials from here itself. Fluid will be air, water, and methanol. By default, only the air is there. Now we need to define water and methanol. That will be obtained from Fluent database. Initially, we'll select water, copy. Next to that, we have to select methanol. We'll be providing methanol in vapor stage, copy, close it. And the solid material we are keeping as aluminum as default, as this is not a heat transfer problem, so material will not be having any kind of interaction with these fluids. Let us close it. Next to that, we can see models. Multi-phase should be on. In this multi-phase model, we are having 4 different options like VOF, mixture, wet steam, and all-area. Among these different options, all-area is the best one. To have better accuracy, you can have all-area. We have already performed an analysis with VOF. Next to that, I'm gonna apply mixture, and finally, after getting mixture, we'll do for all-area. Okay, so we're taking mixture from here, and implicit body forces should be included to consider surface tension and gravitational effect. Number of all-area phases should be 3, as inside this container it will be having air, and from 2 entries will be providing water and methanol. Let us apply. Next to that, you can see different phases. It is consisting of 3 phases. Primary phase is consisting of air. That is, default fluid is air, and we can rename this one as air. Let us apply. So primary phase already you have considered as air. Let us consider secondary phase. It will be made up of water, and we can rename this one as water. Constant diameter of 0.01 millimeter. Let us apply. Finally, we have to select phase 3 as methanol vapor. We can rename this one as methanol, and we can edit this one as methanol with a constant diameter of 0.01 millimeter. Let us apply. Next to that, we need to see the phase interactions, and we need to provide values of surface tension. Surface tension with force modeling should be on, and wall addition should be checked in to provide better boundary layers. Now you can see the different options are available, like coefficient of drag and by the same time we are having some slip velocity and surface tensions are also provided, right? So we'll select the surface tension as constant, and other values will be providing as default. We're not providing these things. That can be provided as per requirement. The slip velocity and drag coefficient can be provided as per the problem specification. At this moment we are providing surface tension only with a constant value of 0.01, that is in between air and water. You can provide these values as per your requirement. Apply. Next to that, you need to select air and methanol, and we need to provide those values of surface tension and other values like slip velocity and drag coefficient. Let us consider surface tension to be constant, and we will provide this one for air methanol. It will be 0.05. Apply. And finally, for water and methanol, we need to provide these values as surface tension should be constant, and this value will be 0.9. Let us apply and close. And the viscous model should be K omega 2 SST. Next to that, we need to provide boundary conditions. We're having two inlets for different fluids. From cap 1, we'll be providing water at a specific rate. Let us provide water at a specific velocity of 10 meter per second. We're considering the velocity of water as 10 meter per second. And for multiphase, we can select that the volume fraction of water will be 1. That is 100% of water will be passing from this opening. No methanol will be there. It will be only water. So volume fraction of this one is 1 and velocity is 10 meter per second. You can see other things like methanol, it should be having 0 volume fraction. Let us check that one. In inlet 1, we are having only water with 100% volume fraction, and methanol should be having 0 volume fraction. Close it. Similarly, air is a default fluid. So air is the primary fluid and it will be inside this container initially. So we can provide only one thing, like velocity of air can be provided, but we need not provide any velocity of air. Let's close it. Now let us see cap 2. From cap 2, we have to provide methanol at a specific velocity again. We're considering the velocity of methanol should be 30 meter per second. And for multiphase, you can see that volume fraction of methanol should be 1. That means from that opening, we are providing only methanol. Apply and close. We can see at cap 2 opening, water should be having 0 volume fraction. That means from cap 2, we are providing only methanol, no water. So we can check it that from multiphase, volume fraction of water is 0 at this location. Inlet conditions are satisfied. Next to that, we see outlet. The outlet pressure should be 0 gauge pressure. Let us see that one. So at outlet, gauge pressure we're considering as 0. Let us apply and close. Done. And we're having a lot of walls. As it is a fluid mixing problem, we are not having any kind of interaction with the walls. Only some boundary layers are formed. So heating effect will not be required in this case. Walls will be required for only providing boundary layers only in this case. Next to that, we have to select methods. And we'll be considering PISO method. It will be started with Green-Gauss node-based method. Momentum should be third order MUS cell. Volume fraction should be quick. Turbulent model should be third order MU cell. Next to that, we need to initialize. And we can start initialization as a standard initialization, and it will be complete from all zones. And initially, the container will be filled up with air only, and that will be provided here. That means initial volume fraction of water should be 0, and that of methanol should be also 0 at initial state. Let us initialize. Next to that, we need to check calculation activities. We'll save data file every 50 time steps. Next to that, we need to run calculations, and we are considering 100 numbers of iterations, and time steps size is 0.01, and maximum iterations time step equal to 5. Let us calculate. Solution phase is over, calculations are complete. Next to that, I'm going to see results, and that can be viewed from here. Initially, we will see dynamics of flow particles, and from there we'll see the different volume fraction of methanol and water. So we'll see path lines, insert new path lines, and from particle variables we'll see dynamics of flow particles of methanol. Let us have a pulse of it. This one is showing dynamics of flow particles of methanol. And the volume fraction of methanol is very less. You see from left hand entry we are providing methanol, and from right hand side we are providing water. This is a transient analysis. Let us stop it. Next to that, you want to see dynamics of flow particles of water. Let us have a pulse of it. This one is showing volume fraction of water. Let us stop it. Next to that, I'm going to show different pressure velocity distribution through front plane. Let us create a plane surface on XY plane. And on that plane surface, we're going to see different contours of pressure velocity, contours of pressure, through plane number 9. Let us display. You can see pressure distribution. Pressure at the entry of water, it is very high, and you can see average pressure is maintained throughout this surface. Average pressure of 2.8 into 10 to the 3 Pascal. And you can see at the inlet of water, its pressure is in the range of 6.8 into 10 to the 3 to 8.9 into 10 to the 3 Pascal. Next to that, I'm going to change the contour from pressure to velocity. Let us display. You can see velocity distribution through front plane, and this is the intersection where both the fluids are being mixed, right? Let us close it. With this one, we will conclude our today's analysis of fluid mixing. This is a very simple fluid mixing analysis using ANSYS Fluent watertight geometry. Through this analysis, we have seen volume fractions of water and methanol. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.